there we go. So Coral Reef Watch it has been around since the 1990s. And I was involved in Coral Reef Watch from 2005 until 2021 while I was still working at NOAA. So very often I'll refer to we. It's not we anymore because I'm retired from Coral Reef Watch and I haven't been working there. But understand that the we is talking about the group at Coral Reef Watch rather than what I'm doing myself personally. But anyway, it's interesting to know where this came from. And so the first half we'll be talking about the projects that led to Coral Reef Watch and the earlier developments up until almost the products that are being used today, the products up until about a year ago. And it's mostly going to be on the development side. And then we'll take a break. I'll answer some questions, and we'll speak after that about some applications of the products. So with that, go ahead and get into it. As I said, we'll talk about the origin of Coral Reef Watch's bleaching products. Peter Glenn, professor at University of Miami, or professor emeritus at University of Miami, and his initial experiments in the Eastern Tropical Pacific. Then what went on at the U.S. Naval Academy with student projects on bleaching, how that led to the actual Coral Reef Watch initial products, which were 50-kilometer resolution products. Then the move into the 5-kilometer products, and a little discussion of the climatologies used in that, which are quite important, as well as the model-based Outlook product. So for those of you who aren't familiar with coral bleaching, this is the same spot. On the left was December 2014. The right was February 2015. We'd seen major increases in temperatures in this case in American Samoa. When high temperatures stress corals, it causes a breakdown of the symbiotic relationship between the coral animal and the microscopic algae they'll refer to as zooxanthellae that live in their tissue. This breakdown in the relationship causes the corals to expel the algae. They don't digest them, they actually expel them out into the water. This leaves the corals white. It leaves them non-photosynthetic, so they're no longer able to produce food on their own. It also leaves them susceptible to disease as a result of this, and just because of the high temperature stress as well. Coral bleaching corals can recover from bleaching, but yeah, they are damaged and stressed. It can have an impact on their reproduction for a couple of years. It can, of course, increase chance of disease and mortality. And of course, when corals die, they're gone and have to be resettled by new recruits. Recently, we had a major event. This was the third global coral bleaching event. We'll talk about this more in the second half. This ran from 2014 to 2017, was the first time we've had a multi-year global coral bleaching event. And as you see from the illustration below, the heat stress being seen mostly in those dark red colors is moving back and forth between the two hemispheres as this event goes on. This is a recent manifestation of what was seen early on, starting in actually the Eastern Pacific in 1982 and 1983 during that El Nino. Now, in 1982-83, there was a major El Nino going on that was heating up temperatures. Peter Glenn had actually was just preparing to leave from his job he'd been at the Smithsonian Tropical Research Institute in Panama and moved to the University of Miami, where he retired just a few years ago. In that work, he had been working in Panama and Costa Rica and down in the Galapagos, working on various types of corals, coral reef communities. And what he found when he went out onto the reef was something very surprising. The places that we'll talk about first, where this bleaching was seen, was at Uva Island. It's actually a very small reef on the north end of this island you see in the lower left. That island is a little speck in the Gulf of Cherokee, north of the island of Coiba. And the Gulf of Cherokee is important because you don't get full upwelling there, but you get thermocline shoaling. So temperatures, the cooler thermocline can pull upwards to near the surface, or it can be really depressed, but you don't actually see that thermocline breaking the surface during cold events, as compared to the Gulf of Panama nearby, where you actually see the temperatures getting very cold up at the surface. Well, what happened was he went out to do some regular work, not expecting anything unusual, and he saw that the reef, as you see from these black and white photos that were published in this paper in 1983, that a lot of the reef had suddenly turned white and died. Those corals had not only bleached, but they had gone through a rapid death, were overgrown by filamentous algae, and led to a lot of impacts on the reefs there in the Eastern Pacific. These pictures being from the reef at Uva Island. If you look at the paper that he first put out on this, it talks about, just a second, there we go. It talks about, back up, come on, let's go back. Okay, I'm gonna have to back up a second, hang on. There we go. Talks about how in the Eastern Pacific, extensive bleaching and death of corals were reported in the Galapagos Islands, in addition to Panama, and eventually found Costa Rica and elsewhere as well during that same period. And what you'll see in this original paper in Environmental Conservation suggests could have been due to copper mine project, dam construction, oil, pesticides, although there had been some other disturbances at the time, such as low tidal exposure, El Nino leading to warm temperatures, earthquakes, but no causative agent could be identified at that time. They really weren't sure what was going on. Peter was looking through, trying to find information about what was going on and why these corals died. Well, at the same time, in the early 80s, NOAA had just started producing images of data and images of sea surface temperatures from satellites. This was in the very early days of satellite sea surface temperature. And these images from a paper of his in 1988 look back at that time during 1983, and you're looking at the sea surface temperatures and the impact that that had with the El Nino conditions on the left and the La Nina conditions on the right. El Nino, of course, is a large-scale oceanic phenomena that leads to major atmospheric impacts. It results when the winds change and the current patterns change such that you get warming in the eastern tropical Pacific. La Nina is just the opposite. You get cooling in the eastern tropical Pacific. And so within about a year of that 1983 paper, it had been identified that indeed what was going on was that there were really high temperatures at that time, and that may have been the reason. Well, Peter decided he wanted to do some experiments, and in fact, right at that time, he was submitting a proposal to the National Science Foundation for multi-year work. And one of the things he wanted to do was to run experiments on the heat stress and if that was causing the bleaching and mortality of the corals. Note to all of you students, don't always believe what you hear from a program manager. If they say that you don't need to run an experiment because it really isn't worthwhile, you might end up finding a way to do it anyway. And that's what Peter did. He had actually been told by some that there's no real evidence the temperature was that big a deal, and from others that sure, if you raise temperatures enough, it can hurt any organism. But this really doesn't make sense as a project. He went through and he exposed corals that were sourced from both the Gulf of Cherokee and the Gulf of Panama to various temperature regimes. You see on each of these plots, which are looking at the zooxanthellae versus various parameters to normalize them. That the temperatures were, for the Gulf of Panama corals, were run at ambient temperatures at 28 degrees, 30, and 32 degrees. The Gulf of Cherokee, they were run at ambient 26, 28, and 30. And what you can see is that, in fact, at the higher temperatures, you get a lot of bleaching that occurs, a lot of mortality of the corals as well. This paper, which reviewers had said was work that didn't really need to be done, ended up getting the best paper award in the journal Coral Reefs for that year. So again, sometimes reviewers don't know the best thing that's going on, and science can and should go on despite what reviewers say. Anyway, some other work going on at the same time was looking across at the Caribbean, in this case, Northeast Caribbean and Straits of Florida. You're looking at sea surface temperatures and seeing what's going on with those temperatures and how they compare. And seeing that, of course, average temperatures from one place to another are rather different and that difference can be identified using satellite sea surface temperatures. Some of this work was being picked up by Al Strong, who you see here in the background. And when he started working as in an assignment from NOAA over to the US Naval Academy and was teaching there. The gentleman in the foreground on the right is Midshipman Michael Gleason. You'll be hearing about more in a moment. He started working on coral bleaching and how satellite data could be used to get at this new problem that had been heard about called coral bleaching, because there have been many bleaching events that were going on in the Caribbean, but it really wasn't seen as a major global problem at that point. Well, a couple of students, Midshipman Richard Montgomery and Midshipman Michael Gleason, both worked on projects. Here you see posters that they did working with Al Strong on this. And the one on the lower picture down here, the correlation of coral bleaching events and remotely sensed sea surface temperatures, really started getting attention. And another thing that was going on at the same time, as was very political as we are right now going through the preparations for an election. 1992, there had been an election where Bill Clinton and Al Gore were elected into the White House. And Al Gore was very interested in science, was very interested in these new discussions about climate change and the problem of global warming, and would have regular breakfasts with scientists as a part of it. He had also held Senate hearings on coral bleaching when he was a senator prior to being elected vice president. And so one of these breakfasts that he invited along some scientists to meet with him and discuss this problem of coral bleaching. Here you can see Al Gore in the center, Midshipman Michael Gleason to his left, Al Strong here, and Peter Glenn, all meeting with him over breakfast. What was originally supposed to be a 15-minute presentation by the midshipman turned into an hour-and-a-half discussion with a vice president who was very excited about this new problem, environmental problem that was coming in that was related, or perhaps related, to global warming. Well, this led to Al Strong continuing to work with other students and then pulling together some people when he was pulled back into NOAA from the Naval Academy, and started looking at this problem of what was going on with these temperatures and why the high temperatures cause corals to bleach and how you might be able to bring this into satellite products. One of the things that was realized, and they developed the first product, was called hotspots. Hotspots were how much warmer it was than the temperature those corals normally see. And it was the realization that it's not just the temperature, but it's the size of these anomalies that matters. The hotter it is above the normal temperatures, the more impact it has. And it also depends on the temperature in different places. Different places have different average temperatures. And so that can influence how you develop these products. Here you can see it, more of that work that was done early on. Michael Gleason, the Gleason and Strong paper from 1995, where you can see on the left in Bermuda, the average temperature is, maybe about 23 degrees from that. The average temperature in Jamaica, 27, 28. And so when you look at that, you'll also see, whoops, sorry about that. You'll see that the time that those bleaching events and the temperature of those bleaching events are very different from one location to another. And so this led to the important fact that if you're going to be using satellites to give you data on coral bleaching or an index of potential coral bleaching, you had to vary this by location. So each location had to have its own climatology that you used. So this led to the original product, which was this hotspot product. And you were looking at a climatology that was called the maximum monthly climatology, or the maximum monthly mean. The maximum monthly mean was the average temperature of the warmest month of the year that the corals encounter at that location. So at any spot, you figure out what the warmest month is, you take the average temperature of that warmest month, and that's something that corals see on an annual basis. You then take the current temperatures and you subtract the climatology from that, and you get a positive only anomaly that just looks at how hot it is for those corals. Thus, the term hotspot. But hotspots weren't enough. It really was important to also understand how long the corals were exposed. The x-axis that's cut off of this is that the bottom is time. And so the longer corals are exposed to a given temperature above their normal temperatures, the more impact it had in terms of loss of zooxanthellae, loss of chlorophyll, impact on bleaching of the corals. And in fact, some of that work that Gleason and Strong did was to look at this degree heating week idea, how you do coral bleaching as a reaction to heat, but not just heat, but to heat stress that builds up over time as a dose response sort of thing. So it's an accumulated anomaly, a set of anomalies. And as Andy mentioned earlier, it's an accumulation over 12 weeks of these hotspot anomalies with an added twist. And I'll get to that in a minute when we talk about how the products are actually made. But early on, seeing that as the temperatures increase and how long they increase makes a difference. And for bleaching, it's a combination of both the temperature, or I should say the anomaly, as well as how long you're at that anomaly. So that took the hotspot product that was already in place, and they started developing how to add this up. Now the hotspots, as I said, you're looking at temperatures. The black dash line here is the average temperature of the warmest summer month. That's your maximum monthly mean climatology. Anytime temperatures get above that, then you have these hotspot values. Well, if you just take all the temperatures and start adding them up, you get a lot of times where you get a little bit of temperature above, a little bit of temperature above, and it starts getting a little squirrely to work with the data and the results that you get. And so as a more reliable method, what they did, they said, all right, we're just going to take these hotspot values that are 1 degree C or higher. So 1 degree anomaly is the threshold at which point we'll start accumulating these through time. And this area where they're more than 1 degree warm, warmer than the maximum monthly mean, is the period when the hotspots were accumulated for this degree heating weeks. And it was the entire temperature that was then used. So you took those temperature excursions and you added them up through time, and so you have the sum of 12 weeks of all of those values, and that then creates this degree heating week product. And Andy mentioned this in his attribution discussion. For this, and for a long time, up until about a year ago, the product really looked at hotspots at two critical thresholds. 4-degree heating weeks was when coral bleaching was expected, and 8-degree heating weeks and above where you expected coral bleaching and the onset or widespread coral bleaching and the onset of coral mortality. So that was the degree heating week product, and this became the first and most really important of the products because it was much more predictive of coral bleaching and continues to be much more predictive of coral bleaching to this day than anything that's just based on anomalies without having that accumulation through time. So these were the products that were used starting in the late 1990s and were really used until about 2015. The products were actually run until 2020 because we wanted to keep them running as long as we could to keep using them, accumulating data to compare what came later, the new version, against the older version. So we understood what was going on in the change. So let's look at what these products were and how they were computed. The climatology was a 7-year climatology. That was really all that was available when they started developing these products in the 90s, because the data were only available since 1985. That was when the widespread use of the polar orbiter data became available, and the kinks had been worked out of it. They'd actually been running the satellite since 1982, and so the satellite data were available from when that bleaching was going on that Peter Glenn saw. But they weren't stabilized well until about 1985. The data were using these polar orbiting satellites. At the early time, there was only one satellite flying. These were operational products, but only the nighttime data were used, because what you find is that during the daytime, the high temperatures at the extreme surface of the water, which is a very thin veneer of microns that is what the satellite actually sees, would really change dramatically, and you get a much higher temperature during these high temperature periods than the underlying water, even just a meter down. So the nighttime temperatures were much more reflective of what was being seen in the water that the corals were seeing. So thus only the one-time single scene per night data were being used. But because of the way that this satellite works, it does get daily overflights. So you did have data coming in once in the daytime, once at the nighttime at the same time. These were stable orbits. I believe they were passing at about 4 o'clock in the afternoon and 4 o'clock in the morning. And you would have these data coming in. And that's what was used for probably close to 20 years while the products were in their earlier phases. Talking about satellites, we're going to come back to this in a few minutes, but there are two types. You've got geostationary weather satellites that sit in place, and then these polar orbiters that span the entire globe. The geostationary weather satellites had temperature measurements on board, but they were not stable enough, reliable enough, or high enough resolution to really use for this purpose during the early period. So only the polar orbiting satellites were being used, and there were only a couple that were being used, a couple of NOAA satellites in the early period. That changed as we went through time, and you got a larger constellation of satellites. But what were some of the problems we were running into? Well, one of them with a 50-degree product is 50 degrees is pretty coarse. You think about the size of I mean, it's not 50 degrees, 50 kilometers. You think about the size of a 50-kilometer pixel. That's a lot of area. And because you didn't want to use data that were contaminated by land, often it was well offshore. And so as a result, if you look at in here at this, this is Puerto Rico. You've got Dominican Republic on the island of Hispaniola here. You've got Puerto Rico here. You don't even see the US Virgin Islands at this resolution, but you see some of the other islands that are in the island chains. The data are well offshore, they're very low resolution, and they work pretty well for coral reefs despite this, but that was a real problem, and there was a desire to get A, closer to the reefs, and B, higher resolution. Another thing that would happen is because you're only using that single nighttime scene, you could get some strange things happening. These were the 50-kilometer products using the regional virtual station in Thailand, at Tao Island, where you see that the degree heating weeks started accumulating. That's what this curve represents. And it shows that they accumulated and they accumulated and they just kept going, and they broke the scale of the graph, and we're up in the range of about 30-degree heating weeks, and that seemed absolutely crazy. Well, the reason is if you look at the temperature plot up here, this line is going along, you see the usual changes, and then all of a sudden it's gotten really hot, and right after it got really hot, the temperature was absolutely constant for several months. Now, the temperature was not absolutely constant for several months. What happened was we got into the monsoon season. The cloud cover was so thick that they were not able to get adequate data to bring new data in for that location. And as a result, that high temperature that you had been seeing right before this started was maintained in the data set. And so the data set, the analysis kept using that same high temperature for the entire time until all of a sudden one night it saw this reef. The satellite was able to see this reef peeking through the clouds, and boom, the temperature dropped down and dropped down very quickly. So that was clearly a problem, that only getting those single nighttime views was a real issue, and would continue to be a real issue as long as only one satellite was being used. Now, by this time, there actually were 2 satellites flying, but the operational product only was able to use one at a time. So that was something that could be improved upon, but not dramatically. So what happened was there was a move to develop higher resolution products and solve some of these problems. And so starting in about 2013 was the onset of the use of the Coral Reef Watch products using a geostationary polar blend. So using both geostationary satellites that sat in one place and gave you data all throughout the day, and the polar orbiting satellites that were going around and around and giving you fresh data on a daily basis. Going through and combining the data from actually multiple satellites from multiple countries, not just the 2 NOAA geostationary satellites, but also a European and a Japanese satellite. And then polar orbiters were using 2, but actually that got increased later on and started picking up some additional polar orbiters. And this new analysis had the ability to do this. But to do this, we also needed a better climatology. That original climatology had been a period of 7 years long. It was from 1985 to 1993, but because of problems with aerosols from Mount Pinatubo eruption, 1991 and 92 had to be thrown out. So you only had a 7-year period from about 85 to 93 centered on 1988. And that was something that Andy talked about earlier about, the Coral Reef Watch period being centered on around 1990. It's actually October of 1988 is the center of that original climatology. Well, knowing the temperatures had warmed when the new Pathfinder-based 22-year climatology was put in place, that climatology was actually adjusted so that the mean would be the same as the original climatology. So we weren't shifting the baseline. That if we'd shifted the baseline, that would have dramatically impacted how the products worked. But instead kept that baseline the same by normalizing and shifting those data so that all we pulled out of it was an increase in variability. So this was rolled out in 2013, fully running in 2015, and shortly after that, there was another improvement in the climatology that comes in. So the bottom line in making that change, there was a 100-time increase in spatial resolution, going from a 50 by 50 kilometer product to a 5 by 5 kilometer product, and 50 times more data per pixel. So it was an amazing change in not only the resolution, but the amount of data going in and the reliability of the product. You didn't have that problem any longer, where a given pixel would be blocked out for months at a time. So now, not only were we using the polar orbiters, but we're bringing in these geostationary satellites. And so what that does is that gives you continuous data on an hourly, or in some cases sub-hourly basis at high resolution. NOAA had brought in new geostationary satellites by this time. Other countries had launched new satellites, and they continue to launch better satellites, improving things to the point that now there's some potential to be able to move this to about a 1.5 to 2 degree product in the not too distant future. The other thing was developing new climatologies. So in order to really get a good data set, there was a major effort, multi-million-dollar, and the effort putting together the new sea surface temperatures using both satellites was a multi-year, multi-million-dollar effort. And there was another effort comparable to develop this new climatology that took the data from all of those years from 2002 to 2015 and developing a new baseline. Later, this was expanded and was developed from 1994 to present, and currently is being pushed back into the early 80s. So what did this result in? A whole suite of products at 5 kilometer resolution, starting with sea surface temperatures on a daily basis, with each of these being only a daily product, but it is based on a whole series of observations throughout the night using multiple satellites. The development of sea surface temperature anomalies, or in other words, how different the temperatures are from the normal temperatures on that day. And these anomalies are very important oceanographic products. You see things like these features during some La Nina structure here in 2018. You can see areas of warm and cold on a given day. But for corals, again, you wanted to use that temperature anomaly that was based around the maximum monthly mean. So here you get into the coral-specific products. The coral bleaching hotspot that we spoke about already, comparing the current temperature to the maximum monthly mean. The degree heating temperature that sums those up. And then because most of these products we really continue to work with coral reef managers and folks who are not data scientists, and we get confused and say, well, should I be looking at the hotspot? Well, the better prediction comes from degree heating weeks. Okay, so you just want to look at the degree heating weeks. Well, there's actually really important information to know how hot it is today and what the temperatures are doing now, in addition to what the degree heating weeks have accumulated over the last 12 weeks. So the whole point was, let's do something simple, and the bleaching alert area was developed. Here, you're taking the Earth and dividing the ocean regions into no stress, bleaching watch. That means the temperatures in those hotspots, the anomalies in the hotspot product are less than 1 degree of increase above the maximum monthly mean. Once you've passed that 1 degree and start accumulating degree heating weeks, you get into a bleaching warning. And then at 4 degree weeks of warming, you have alert level 1. And at 8-degree weeks, you get alert level 2. So those are the products that then went on up and were being used up until about a year ago. They were also improved during that time with this next improvement of climatology that used multiple data sets, using the 1985 to 2002 reprocessed Ostia data set from the Europeans, 2002 to 2016 reprocessed NESDIS geopolar blend, which was being pushed back to 1995 and potentially back to 1985. And then the new data going forward, we're using a near real-time processing of the geopolar blend. So this gave the best data set that was available and really was implemented around 2017. So you can see this is the difference between the Pathfinder-based 5-kilometer data set and the new coral temp data set to develop the climatology. And just looking at average temperatures around the world, you can see there are areas that now were identified as being cooler than they had been, some as warmer, and a real improvement in the accuracy when you go through and start analyzing this. But remember, none of these are right. That's the one thing that's important to remember about any remote sensing product. It's never right. It's just the closest you can get with the methods that are available and the technology that's available. Here you can see the impact that it had in a very important time, the 2014 to 2017 third global coral bleaching event. Using the old climatology, it said, well, it's warm around the northern Great Barrier Reef, but not that warm, when in reality, corals were dying hand over foot all throughout the northern Great Barrier Reef. With the new climatology, we were able to identify that and predict it properly. So this is one of those areas where there was a great improvement. So talking about one more product, the degree heating week was an accumulation of data from the sea surface temperature from the satellites. And this is very useful to tell scientists and managers what is going on. But the question was always, what's going to happen in the future? And so the next step was to use climate models, taking various climate models and bringing in the data from those and developing the same thing, looking at that time of the excursion above the maximum monthly mean and adding that up to be able to generate degree heating week products from the satellite, from the climate models. And it found that for most of the time can pretty reliably predict up to 4 months in the future. In some cases, when there's a major El Nino event going on, some regions of the Earth, you can reliably get up to about 6 months. That's a little tougher. But anyway, this is the product that came out of that work, which is using the National Centers for Environmental Prediction, NCEP's Climate Forecast System Model V2, to predict future coral bleaching. This is for a period back in 2012 that we're looking at. And you can generate all of your various products, your watches, your warnings, alert level 1, alert level 2, and the probability of those various levels of heat stress at any particular time. So this gave people, especially managers, the opportunity to be able to look and say, hey, there's going to be an issue in the future. Scientists could get out and could plan to get out and do more surveys, plan trips to remote locations to check for bleaching. Things of that sort could be done. And there's more that managers could do. And we'll talk about that later when we get to the application section in part 2 of this talk. So with that, I'm going to pause and give us a chance to give you a chance to ask some questions. And let me stop share here so I can see y'all. All right, so any questions on part 1? Remember, applications are coming up next. No questions? All right, well, we'll go on into part 2 then. And if you think of questions related to the products later on, that's fine. We'll answer them all at the end. Oops. All right, so in this one, we'll be talking more about various ways of monitoring reef health and what can be done with these products, how they can be used. And a portion of this is going to talk about this big bleaching event that we were just talking about a moment ago, the global coral bleaching event that lasted from 2014 to 2017. We'll talk about how that fits in, some of the things that it's been applied to. We'll talk about the current and ongoing 4th global coral bleaching event that just started last year. Hopefully will only be 2023 to 2024, but it could be a multi-year. We'll get to that too. We'll talk about how bleaching forecasts can be used to protect species and talk a little bit about some of the latest things that Coral Reef Watch has been doing that are available as well. So again, back to those basic products that are being used, the sea surface temperatures, the anomalies, the hotspots, degree heating weeks, and most of the graphics you'll see will be these bleaching alert area charts. We'll also be talking about the forecasts. And this is the coral bleaching outlook. This is the current one from this week. You're looking at September to December of 2024, and you can see that there's a prediction for a lot of bleaching level heat stress coming up in the rest of this year. And we'll get to that when we talk about the current ongoing event. So what happened in 2014 to 2017? Well, in 2014, 2015, there was what looked like was going to be the development of an El Nino. And there were forecasts from NOAA and others about a potential 2014 to 2015 El Nino. As temperatures were warming during this period, we started seeing heat stress coming on in 2014, which is in the period leading up to the El Nino, which is actually unusual. Most of these areas see bleaching at other times. Marshall Islands and Florida are often seen as a bleaching in the second year of an El Nino. All El Ninos are a 2-year couplet because they'll start late in one year and go into the next year. Guam and Marianas very often are tied to La Nina conditions. And Hawaii has never really had an El Nino related pattern at this point. But we started seeing a lot of bleaching going on in parts of Micronesia, the Marshall Islands, Guam, the Marianas, the Northwest Hawaiian Islands, and in South Florida in the latter part of 2014. Going into 2015, expecting an El Nino, one thing we started looking for was a pattern that had been seen previously. 1998, which was the first global coral bleaching event, was a period where there was a lot of observation of coral bleaching. And this paper by Ove Hugelberg in 1999, you can see the dates where initial observations of bleaching began. And if we go through and sort of track this forward in time, what you see is it was sort of Eastern Pacific to the Great Barrier Reef, across into the Indian Ocean, into Southeast Asia, and then later jumping back over into the Caribbean. And that was that pattern that they had seen in '98. We saw another global bleaching event in 2010, and it followed that same sort of pattern. First, you saw it as a part of the El Nino warming in the Eastern Pacific. Then you started seeing Australia, Indian Ocean, Southeast Asia, and last would be the Caribbean. As I said, it was unusual that we were seeing bleaching in the Caribbean as a part of 2014's lead-in into what we thought was going to be an El Nino. Well, as we move into 2015, we saw this pattern again. As the warming happened, we saw, not in the Great Barrier Reef, but we saw bleaching in the South Pacific and American Samoa and Fiji, across to the Indian Ocean, actually to the southern Indian Ocean, then to the northern, then to Southeast Asia, and later jumping across into the Caribbean, and at the same time into Hawaii. Hawaii was unusual. This was the first time there was a major bleaching event on the main Hawaiian Islands. And we'll come back to that in a few minutes. 2016, we saw the same thing. Now, 2014, 2015, there was never actually an El Nino. It never fully materialized. Some of the warming happened, the winds never shifted, and so there was no 2014, 2015 El Nino. There was, however, a 2015, 2016 El Nino. And as we got into 2016, we started seeing a lot of heat stress in the Eastern Tropical Pacific, Great Barrier Reef bleaching, Indian Ocean bleaching, Southeast Asian bleaching, and Caribbean bleaching. In fact, this was the worst heat stress, the worst bleaching that had been seen on the Great Barrier Reef. A number of papers came out as a result of the work that we did on this, mostly led by Terry Hughes. Here you're seeing the relationship between the heat stress on the right and the bleaching patterns on the left. Later, looking at change in cover as an indication of mortality of corals. And again, heat stress on the right, change in cover in this case, or mortality on the left, and saw 29% mortality of corals across the Great Barrier Reef during 2016. This was the worst bleaching and the worst mortality ever seen on the Great Barrier Reef. It's a photo from the Lizard Island Research Station, one of the premier coral reef research stations in the world. This quote from Justin Marshall at University of Queensland: "The lack of fish was an indication that there was complete ecosystem collapse. What had been a vibrant coral reef just turned into a wasteland. Fish were gone. Many organisms were dead, dying, or left. No idea where they went." Well, in addition to all of the scientific observations, one of the things that came out because of this event was this film, Chasing Coral. I hope you've all seen it. If you haven't, watch it. It's available on Netflix. It won the 2017 Sundance Award for Best U.S. Documentary, won the 2018 Emmy for Best Nature Documentary. As I say, it's streaming on Netflix. I'm sure everybody there has a Netflix account or somebody else's Netflix password. And if you don't want to do that, it is available actually for free on Netflix's YouTube channel. A couple of years ago, on Earth Day, Netflix took a whole series of their best nature documentaries and made them available for free on YouTube, and have left them that way, which is great. The work that was done in the movie Chasing Coral, being able to get out and film what was going on the reefs as they bleached and died, was only possible because of those advanced forecasts of coral bleaching, knowing where to go, what was going to be happening, and pulling teams together to go out and capture it on film. They captured what happened through the 2016 bleaching event. So that major bleaching in the Great Barrier Reef that we were just seeing, including what you saw in Lizard Island there, was captured in the film. The film was released at Sundance Film Festival in February of 2017, right as the Great Barrier Reef was bleaching again. What we saw in 2017 was bleaching on the Great Barrier Reef, the second worst bleaching that had ever been seen, moving across into the South Pacific, and the Southern Indian Ocean, and then kind of fizzling. There was some bleaching later on in the Marianas and and the Micronesia. There was also bleaching that occurred in the Caribbean. But that full cycle of bleaching pattern that had been seen in the previous global events didn't happen in 2017, and really was considered that in 2017, about May of 2017, when it was in the bleaching ended in this southern Indian Ocean, to be the end of that 2014 to 2017 bleaching event. Great Barrier Reef, as I said, 29% mortality in 2016, 22% mortality in 2017, another severe event, and in different locations. Here you can see that in 2016, the worst bleaching was at the far north and northern part of the Great Barrier Reef, whereas 2017, it was more a central Great Barrier Reef event with some bleaching up in the north as well. But because some of these areas had been exposed on the Great Barrier Reef in both 2016 and 2017, we were able to see some patterns of how that affected things. In fact, as we look at what happened in 2014 to 2017, this was the longest global bleaching event ever. Over half of areas were exposed twice. Guam actually saw 4 out of 5 years in a row exposed to reefs, coral bleaching. It was the most widespread event ever. The area of coral reefs affected by this event is larger than the state of Washington. Over 2/3 of reefs suffered bleaching level heat stress, and it was probably the most, or almost certainly the most damaging on record to that point. Now, as mentioning the Great Barrier Reef, looking at 2 years of bleaching, this was one of those places where we had back-to-back bleaching. And so we were able to look at what happened on the same reefs in 2016 and in 2017, and looking at the probability of bleaching. So if you look at this figure on the left, here you see the severe bleaching in 2016. It was higher than in 2017. But if we take the data and we look at the right side at what happened in 2017, and compare reefs that were exposed to heat stress or not in 2016, you can see that on those reefs that had no heat stress, that's what the 0 in 2016 is referring to, there was a lot of bleaching that was happening across those reefs. As you go to reefs with higher and higher heat stress in 2016, you see a depressed curve, that there actually was less bleaching going on for the same level of heat stress in 2017 if those reefs were highly exposed to heat stress in 2016. So you had a combination of things going on. One, the most susceptible corals died in 2016. Those that survived were less susceptible and were able to tolerate higher temperatures. And there was some degree of acclimation going on in corals where they actually were better able to survive because of previous heating. And this is valuable information that's been used in some of the conservation efforts since then, in understanding that exposing corals to heat stress that doesn't kill them can actually be useful in making those corals more tolerant in the future. A lot of data was pulled together throughout this, and we pulled together over 15,000 surveys of bleaching, non-bleaching, and mortality. The summary paper on this, didn't revise this. It is actually back in review in Nature at this time, and it's been in review for a few weeks, fingers crossed. As a part of this analysis, what we're able to see were major changes that happened. How, looking across the globe, you could see different impacts of bleaching. Here you're looking at degree heating weeks across the x-axis and the probability of bleaching. You see the 2015-2016 had the sharpest curve. 2014, there was not as much heat stress. 2016 was a bit lower than 2014 and 15. And these curves actually varied by location. When you looked at the Asia-Pacific region, the Caribbean region, and the Indian Ocean Middle East, you saw very different curves and what the impact was across those 3 years in those basins in terms of how susceptible the corals were to bleaching at the same amount of heat stress. We've been able to use that then to confirm that indeed the 4 and 8 degree heating weeks and the addition that was developed for 16-degree heating weeks are really useful levels to look at for the impact that high temperatures and the accumulation of heat stress has on corals and the probability of bleaching. And similarly, looking at that in terms of the impact that it has on the probability of mortality of corals. So it's very, while it was a horrible event, it was very useful in testing some of the products that have been used by Coral Reef Watch for many years, and seeing how they worked, where their problems were, etc. Interesting when you look at this, 2016 was not the strongest El Nino. 2016 falls down here. You look at the really big El Nino in 1982 and 83, and the one in 1998, 97, 98 El Nino, as well as a couple of others in between. 2016 was really not that impressive. It was very hot at the very beginning of the El Nino when the development was there, but then overall it was not that impressive as an El Nino. But it was sitting on top of 1 degree C of warming above pre-industrial conditions. So because we've already seen 1 degree C of warming, the impact of that same El Nino can be much more dramatic in its impact on coral reefs. This is very important when you think about the treaties that have been put in place, the negotiations regarding different temperature anomalies, and trying to stay within them, where the Paris Accord calls for keeping temperatures below 2 degrees C of warming, and with a long-term plan to stabilize at 1.5 degrees or less. We're seeing all of this already at 1 degree of warming. So just imagine what 1.5 and 2 will do. If you go through and look at these past events, 1982-83 was a dramatic event, but was not considered a global event. We're looking here, the black are both alert level 1 and alert level 2 conditions as measured as the percentage of reef pixels around the world. The red are alert level 2 only, so the more dramatic events. You can see that 97, 98, much higher impact. A lot more coral reefs around the world were affected by high levels of alert level 1 and 2. Actually, alert level 1, because you see alert level 2 conditions weren't that high. The second global event in 2010, actually not as high in terms of alert level 1, but higher alert level 2 conditions. And you're really seeing what's going on here is an increase in the baseline temperatures. And so I think you're seeing much more of an effect of global increases in ocean temperatures on the alert level 2 conditions. And then you look at 2014 to 2017, whether you're looking at the total event or each of the years separately, much more impact, very dramatic event. Plus, it was the first time that we've had a multi-year global bleaching event. Now, you may ask, what can you do if you know bleaching is coming? Well, one of them is that you can go out and study them better. One of the things that was done in some areas, Thailand, for example, closed a number of its dive sites, not allowing dive boats to go out to coral reefs to reduce the local stress at the same time that the high stress was going on due to the El Nino and climate change. So, these are some of the actions that have been taken to help corals survive these events. One of the bigger things, though, that we found came along as an example in the main Hawaiian Islands. I mentioned to you before that in 2015, the main Hawaiian Islands saw their first major bleaching event. Back in July, we were looking at the climate models, and the 60% and even the 90% probability models were indicating that there was going to be a lot of heat stress in the main Hawaiian Islands in 2015. Started talking with folks. People were very concerned. They started putting together programs, planning for this major event that hadn't been seen before. One person spoke to me when I was doing this briefing call with people from across the state Department of Natural Resources, and said he'd been talking with a local oceanographer there who said that because of the trade winds that keep local upwelling going, there wasn't going to be any major problem with coral bleaching in Hawaii, that this just was not likely to occur. My response was, I hope they were right. But this is what the models were saying, and the models have never said this about the main Hawaiian Islands before. Well, what you find is this is the actual degree heating, the actual alert area values. You saw alert level 2 conditions on much of the main Hawaiian Islands, severe bleaching, severe mortality, a lot of corals lost. What happened locally was that the trade winds shut down for a couple of months. There was basically no wind, there was no localized upwelling, and the heat stress was able to affect the corals. The good news, that guy who had made that comment to me, Dave Gulko, was in a new job with the DAR, the Division of Aquatic Resources, and was operating a nursery. And he decided, you know, if this is going to be as severe as the models indicate, we're going to go out and we're going to collect the 12 most wanted corals. Okay, yeah, normally it's the 10 most wanted poster, but you know, 3x4 makes a nice rectangle on a poster. So the 12 most wanted corals are endemic corals only found in Hawaii, hard to find, rarely found. Collect them, bring them into nurseries in Oahu and in Maui to try and make sure that these corals are preserved in case something happens. And in fact, one of those that we're looking at there, Porites duodenii, one of those endemics that you see in the lower right corner of the aquarium, that coral was wiped out in the field during this bleaching event. No one going out and surveying was able to find Porites duodenii on the reefs where it originally had been seen, found, and collected. It had been wiped out as far as anyone could tell. Well, the nice thing was, because of this ARC project and keeping these alive, and because of work that's been done on microfragmentation of corals, they were able to grow up pieces. That's actually not a solid coral, but it's coral growing on the surface of a pyramid of concrete. And they were able to put these corals back out on this very same reef where they were collected, less than 4 years from the time that they were wiped out in the field. To my knowledge, the fastest repatriation of an organism driven extinct in the field that we know of. Unfortunately, these events just keep coming. Great Barrier Reef had those major events, major bleaching in 2016, 2017. There was another one in 2020. There was another one this year in 2024. So what's happening now? I've mentioned 2024 and bleaching. Well, these are global atmospheric temperature anomalies that NOAA puts together and comparing each year. This is the global temperature difference from average by month. They have data going back about 150 years. And 2024 has continued through the latest data, which are in July, just came out a week ago. These data show that the temperatures are still the warmest on record. Now, it's likely that they're going to be dropping a bit. We'll see at the end of the year whether they stay above the previous warmest year on record, which was 2023. But the thing that we're seeing now I've been using this picture, this particular graphic for many years now. And this year is the first time that all of the 10 warmest years on record were within the last 10 years. And the way things are going, it looks like we're going to keep stepping in that direction, keeping the last years as the warmest. So that means the background temperatures that the corals are seeing, that the climate system is seeing, that the oceans are seeing from the atmosphere, and the atmosphere is seeing from the ocean, is all warmer than what we've seen in the past. And that gets into that effect that climate change is having on temperature and climate events. Now, it's most likely that La Nina is coming back, and we've seen a breakdown of El Nino conditions already. We've started to see cooling in the Eastern Pacific. Strongly expect to have a La Nina. La Nina does generally lead to cooler global conditions, but not completely. And in terms of coral reefs, there's some areas that bleach more during La Ninas than bleach during El Ninos. So we'll see whether this keeps going around the globe. But the high temperatures that started last year initiated what's been identified now as the fourth global bleaching event. This also led to a change in the Coral Reef Watch products. I said I was going to talk about some of the other products. This is looking at the alert level, the bleaching alert level graphics from last November. The problem that they realized is just using up to alert level 2 really doesn't show you any of the variability that was going on in the Caribbean last fall. All you see are warm temperatures above alert level 2 and nothing else. And also with some of the work that's been done, it's been shown that these simple categories of significant bleaching likely and severe bleaching and significant mortality likely that we've been using for about a decade. Actually, those have been in use for over 20 years. We're a little simple from what we knew. So what they developed and Coral Reef Watch released this last December was a new version of the bleaching alert area product that uses alert levels 1 through 5. So it keeps it on the same sort of scale as is used for hurricanes and is used for tornadoes. Bleaching alert level 1 again is anything above 4 degree heating weeks or degree C weeks of stress. Alert level 2 again is still from above 8, but this time it's 8 to 12. And we see an increase for every 4 degree heating weeks or degree C weeks of heat stress. There's an increase in the likelihood of impact on corals and coral reefs. So the new categories, level 1 is reef-wide bleaching. Level 2 is reef-wide bleaching with mortality of heat-sensitive corals. Alert level 3, multi-species mortality. Alert level 4, severe multi-species mortality. And alert level 5, near complete or greater than 80% mortality of corals. Every coral isn't dead, but boy, it gets awfully close. And we saw that during the 2014 to 2017 event, where there were areas that were up to around 20 degrees C weeks of heat stress. So looking at the same diagram for the global coral bleaching event, the third global coral bleaching event, at the top you're seeing that alert level 1 and 2 graph. Below you can see those areas that have particularly high heat stress and went up to 4 or 5. Really for coral reef areas, we're pretty limited. Tropical waveguide region in the nation of Kiribati and some of the corals around there. And a few in the eastern Indian Ocean areas off of Australia, and a little bit up in the Marshall Islands and Micronesia. But there really were not that many reefs that were hit at that time by those higher heat stress levels. In contrast, here's the third global coral bleaching event up top. This is the fourth global coral bleaching event, the one that's going on now down below. And you're looking at the data throughout this year, the year-to-date observations, and you see that this has actually started affecting more corals, corals in places in the Philippines, in the Western Indian Ocean, multiple countries in the South Pacific, and even some parts of the Eastern Pacific and Caribbean have already been hit at that level. And unfortunately, we're expecting the heat stress to continue. This is Coral Reef Watch's current outlook product at the 90% probability, so pretty likely to happen. These models have not been adjusted up to levels 3 and 4 and 5 yet, but still what you're seeing is the very high likelihood of continued heat stress in parts of the Pacific, Southeast Asia, and in the Caribbean, that this fourth global coral bleaching event is likely to be significant and have a lot of impact of a lot of reefs around the world. Oops, sorry, I already showed that. I forgot to delete the second occurrence. Talk about a few other products that Coral Reef Watch is doing based on their heat stress work. One of them is now there are these great satellites that were developed by Planet, and they changed their name. I'm forgetting the name of the company that is flying these very small microsats that are taking images around the world. And those are being used by the Allen Coral Atlas. This is funded by the Paul G. Allen Foundation. Paul Allen being one of the founders of Microsoft, who's put significant money into conservation, including coral reef conservation around the world. And here, this product is taking the combination of Coral Reef Watch's observations of heat stress and observations of potential bleaching on sites by using high-resolution images that compare the color of the corals at any particular time to what the coral normally is, and use automated methods to identify coral bleaching going on out in the field. To my knowledge, they can't identify mortality yet, but at least they have data that are bringing in observations of bleaching. Not so important in some place like Oahu, where you can get divers out to any of those reefs in a fairly short period of time, but very important in remote areas of the world where it's very hard to get divers to, like Kiribati, like parts of the Marshall Islands. There are parts of Indonesia. There are reefs around the world that are very remote and hard to get to, and these products can allow scientists now to look and see potential bleaching based on satellite observations, which is a real win for identifying bleaching and the impacts of heat stress around the world. Here you can see up close that as the satellite goes through and automatically identifies areas of potential bleaching, and in areas like Hawaii, there are teams that go out and check and say, hey, how well is this product doing? And it's turning out to be a very useful product for spotting coral bleaching from satellite observations. Not just the heat stress, but the actual bleaching as it occurs. Other data that have been released, the Coral Reef Watch uses the long-term data from the climatology to develop a wide variety of products. Things like warm season trends of temperatures, maximum heat stress. What month of the year is the warmest month of the year, and the one that's used in the products. Various trends, changes in variability, all very important observations that can come from these satellite data now that they've been consistently reprocessed through time back to 1985. And another one that's kind of interesting, marine heat waves. So marine heat waves were something that where the community, especially Habde, was looking at the Coral Reef Watch products and saying, hey, how can we do something like that for other ecosystems around the world? And you'll hear a lot in this workshop about what's gone on in various events. I'm not going to talk through the various examples of how marine heat waves have been used to identify impacts of non-coral reef ecosystems. But it's come full circle that now Coral Reef Watch, using its satellites, is providing one of the NOAA satellite-based methods for monitoring marine heat waves around the world. And here you're looking for August of 2024, and those areas where there are marine heat waves and the severity of those marine heat waves in various places around the world. And in some other work that's been done is applying these high temperatures, as well as other factors that we know, such as local human populations, the reef structure and colony sizes, to be able to predict coral diseases around the world. So not just bleaching, which actually is a disease, it's an environmental disease, just like heat stress, just like heat stroke in people. The impact of high heat is a type of disease, an environmental disease. But biotic diseases that are caused by infectious organisms can be influenced by these factors, and taking into effect a new model and various types of diseases on various species of corals, this new product, set of products has been developed showing the risk of coral disease in various locations all across the Pacific. Hasn't been developed for the Caribbean yet. So far it's only Pacific products that started in Australia and then Hawaii, and now have expanded across the entire Pacific Ocean. But you can go online and at coraldisease.com, pull up these products and see how they operate, what you can get in terms of information on what's going on now or any particular time, and even do exercises on your own to say, you know, how much does a certain amount of heat stress affect corals in that area? What do you need? What are the critical levels? Things of that sort. So just a summary of the things that we've gone through. First, we talked about the development of the products in the first half. Now is more the application of the products during recent bleaching events, especially 2014 to 2017. Talked a little about the ongoing 4th global coral bleaching event and how these products can be based. I will make a big point to thank the Coral Reef Watch team, those people who are working there now, continuing to operate and develop these great products. Derek Manzello took over my role coordinating Coral Reef Watch. Gong Liu has been there from the very beginning with Al Strong. He was hired by Al as a programmer and is still working on Coral Reef Watch products. Jackie, the operations manager, Eric Geiger, develops special purpose products. Those folks are all in the US. The folks at the bottom at Reef Sense, a part of Coral Reef Watch that's in Australia, led by William Skirving on the left, and with scientist Blake Spady and programmer Andrew Norrie, are continuing all this great work. So with that, I'll end the sharing. We can open up to further questions. I saw something came up in the chat, so hopefully we'll have some things that we can discuss now.
Great, thank you very much, Mark. I see Olivia's hand up. Actually, well, there were some other questions. Actually, why don't we go to the questions in the chat box first, and then we'll have Olivia. So I see Drew put in a question a little bit before 11:30. Drew, you there? You want to ask it? Oh, she's not online right now. Okay.
Drew, of course,
well,
Drew was leading those disease products that you saw at the end, and Jamie Caldwell, someone who was a student with her and moved on elsewhere, and has done some great work on those marine disease products. We can come back to Drew's question if she comes back online. If not, I'll answer it at the end.
Yeah, I'll mention one thing about Drew. She was actually on the first dive. with Peter Glynn when they went out on the reefs in Panama and came on the bleached corals, and they had never seen anything like that before. So she was there from the very beginning. Okay, let's go to Alexi. She has a question.
Can you hear me?
Yes.
Thank you for your talk. It was very informative. I wanted to ask if there are any plans to incorporate more drones and other aerial devices that to monitor both temperatures and the actual bleaching on the very remote reefs, especially maybe closer to where the SST data shows that there might be bleaching, to kind of have more accurate data.
There's been talk about that. There have been some tests that have been done in some areas that have the resources for it to do regular drone observations. The problem with drones is most of them have very limited range, and so you could do them in a small area, but not in a large area. So unless, of course, you're going to get something like a global hawk or a reaper without the missiles, of course. And you're not going to be able to fly up and down the entire Great Barrier Reef, much less all around the reefs of Indonesia or places like that. So it becomes a limited tool, but a very valuable tool for this. The surveys that you see where we were talking about the Great Barrier Reef work and the amount of bleaching and the mortality on that as a entire reef scale was being done by aircraft. So those were aerial surveys and people going up and doing that. And at some point, drones will take over that work. We're just not there yet. There has been some development of drones, both aerial drones and autonomous undersea vehicles that can go around the reef for measurements. Because of course, aerial work is only good when the visibility allows. One thing I didn't mention, the current bleaching event is absolutely the worst that's ever occurred in the reefs of Brazil. And the reefs of Brazil are known to be in very murky water. So the ability to use drones would be very limited there. Of course, I did talk about what's being done with the Allen Coral Atlas and the use of these high resolution photographic satellites that are doing providing imagery at meter scale resolution, and the ability to use that. So there are limits to what can be done, but we definitely need more and more of that going in to be able to really monitor coral reefs to the extent that we want.
Yeah, Mark, just following up on that, I'm not sure drones would get you a lot better than what they're getting with those mini satellites, right? I mean, it's hard to imagine much better than meter scale resolution.
Actually, there's work that's been done with some very good work with drones from folks who were at NASA and now at the University of Miami, where they're not only using drones, but one of the problems you have at high resolution is the optics of the moving water surface. And they figured out algorithms where you can do what's called fluid lensing and actually use the irregularity of the movement of water at the surface to give you higher resolution by using multiple images and getting sub-centimeter resolution. But you can only do that on a small scale. So everything's a trade-off. Olivia?
Hi there. Hey there. Thank you so much for your talk, Mark. That was really a tour de force and really compelling learning about these powerful tools for monitoring corals. And I especially appreciated your mention about how different groups are using the Reef Watch data to kind of implement actions, like you mentioned the ARC project in Hawaii, and closing diving areas in the Philippines. So I'm just curious, as an expert in this field, do you see the coral reef conservation community moving towards tactics like that for kind of local scale conservation, or more so kind of looking at assisted evolution approaches and trying to help corals adapt to greater thermal resilience? Really curious for your insights on that. Thank you.
Yeah, I would say it's a both and situation. There's really work going on in both directions, depending on what's happening. Some areas, there are local things that can be done, and there are things that have been done on a local scale to reduce heat stress. So the idea of either pumping cool water or shading reefs is one that especially the Australians have looked into. The Australians are looking into and have been testing these shipboard applications where ships are spraying fine seawater mist into the air to increase marine layer clouds. And it does have some cooling effect because they some early work that Ove Hugelberg and folks did at Heron Island, they put out shade cloth. And the only problem with putting out shade cloth, it worked, it cooled and shaded the corals underneath. The problems were, if there was a storm, you had to figure out if the shade cloth was going to survive, if you could rush out to get it out, removed and so forth. Plus, it was being sponsored by snorkeling tour groups that really didn't want to have these shade cloths in the way. So what they ended up finding was that if you ran solar-powered sprinklers, rainbird sprinklers just going shooting water, making small capillary waves on the surface, it decreased the light hitting the corals just enough to have some impact. So localized effects can be important, but you can only do so much of it, and it's very expensive. On the other hand, there are major efforts that are going on with coral nurseries, and the better ones are doing work to try and develop these super corals, do the assisted evolution kind of work to really develop corals that are going to be able to survive higher temperatures. Even with what's done along those lines, if you look at what happened last fall in Florida, it was catastrophic. There's been a multi-year, they're like, I think 3 years or 4 years through a 5-year effort, tens of millions of dollars, nursery raised corals, planting them out on reefs, and all of a sudden the temperatures got so hot they were rushing out to grab the corals and pull them out of the water to put them back into aquaria to keep them alive because they were all dying in the field. So it's tough. The important thing is, if we don't deal with climate change, all of these others are band-aids that are not going to last. So we have to deal with climate change, but doing these other things is important in the meantime. So it's all hands on deck, all tactics kind of situation at this point. Erica, I see your hand up.
Yes, hello. Okay, great. Yeah, so I am not a coral reef biologist, but I did really appreciate your deep dive into DHW. And I'm wondering if this rings true at all. I feel like based on some of the global maps you showed, if you kind of squint over the last decade or so, it kind of seems like there at any point in time, especially during the summer months in the northern hemisphere, or summer months in the southern hemisphere, that there's an alert 1 or alert 2 somewhere. Does that ring true?
Yeah.
Okay.
We're seeing a lot of high temperatures as temperatures have warmed around the world. Alert level 1 is almost becoming the norm in most places. It's quite unfortunate. Now the good news is, when you have sustained low level stress that's not resulting in mortality, while it stresses the corals and can reduce fecundity, can have impacts on diseases, things like that, it also does lead to adaptation of the corals and the ability to both have and allow to persist mutations in the populations. Different relationships between corals and zooxanthellae. There are so many more things to talk about. One of the big things is there are a whole set of different zooxanthellae in corals, some of which are more temperature tolerant, more heat tolerant than others. But the problem is, the ones that are more heat tolerant also tend to be less productive. And so what we've had in past events is if you have a big event, heats up, the corals that survive have shifted their zooxanthellae to the more heat tolerant species. And over time, those get replaced by the more productive species because, hey, that's kind of how things work. So if you don't keep up the stress, you don't keep up the adaptation, because some of these adaptations are very short-lived. They may be changes in community, they may be ontogenetic changes, they may be changes in the structure of genes that can flip one way or another. There are a lot of things that are very dynamic in these adaptive systems. And so at some point, when the temperatures are warm enough, you get more adaptation than you do in early phases where you just have these occasional events that aren't frequent enough to keep them fixed in the population. So, yeah.
A second follow-up. So obviously this talk was about reef building corals.
Yes.
What can we take from this talk and apply to temperate or cold water corals, if anything?
Yeah, the big impact that we're having on temperate and cold water corals tends to be the issue of ocean acidification, because most of those corals don't have photosynthetic partners. So where you have the zooxanthellae that are subject to bleaching in the tropical corals, most temperate and all of your cold water corals are azooxanthellate, so no zooxanthellae living in them, so you don't have a problem with bleaching. There are other impacts from ocean acidification, changing chemistry of the water, that has a bigger impact on those corals. And the same thing, of course, applies to deep water corals. So, yeah. The nice thing, though, is we talked for a long time about the application of these products elsewhere. And in fact, there were people who were using the Coral Reef Watch products for things like watching where whales were likely to be and turtles were likely to be. That led to other products, and that's sort of a part of what was seen in the marine heat wave products that are developed now. And so there's a lot that can also be learned from what goes on in corals and apply that to other ecosystems and the effect that marine heat waves have on them.